my last video, I talked about how we can determine the state of stress on an element of soil, and most of what we talked about was if you know certain stresses on an element of soil, either principal stresses, you can determine shear stress and normal stress on any plane within the element of the soil. But we really did talk about failure. So what I want to do this time is really just talk about how we define failure in a soil. And for soils, failure happens when you have too much movement, or something starts moving, or you have too much displacement. It just really varies on what you're building and what your tolerances are. There's a really popular way that we describe failure criteria, and it's the Mohr-Coulomb failure criteria. Last time we were talking about Mohr circles and how you can plot them and determine the principal stresses, and how you can use the pole and all that to find stresses on certain planes. But this time I'm going to talk about the criteria that we use to define failure in the Mohr-Coulomb way. Okay, there's two parts to this failure theory. And the first part is Mohr's, the second part is Coulomb's. I'm going to talk about them independently, and then at the end I'll show you how they relate and mix together. For the Mohr's failure criteria, the failure occurs when the shear stress on the failure plane reaches a unique function of the normal stress on the failure plane. So the way to think about this is like friction from kinematics and physics 1 courses. So what you're looking at when you have friction, you have some surface. So this is the classic friction case. You have a block, you have a surface, and those are supposed to be touching, but they're not. Well, they are, but not in the picture. So what you have here is you have, usually the problem comes, you've got some normal force. You have some force pushing this way, and then you got some frictional force here. We'll call that force friction. And what happens here is your force friction is a function of your normal force. So that equals a mu times normal force. And really what that mu is, it's just some coefficient that describes how these two materials interact. If it's really rough, this mu may be higher. If it's really smooth surfaces or frictionless, this sort of approaches 0 if it's extremely smooth. But typically, something between 0 and 1 is what we use for this mu value. So what you're looking at here is when you increase your normal force, this value gets bigger, and then you multiply by a constant mu value, and then your force friction gets bigger. So I guess we could maybe define failure here is when you have a normal force, you have a mu value, you know the force friction. And failure would occur when this force pushes on this block, or when this force exceeds what this force friction is, then the block starts to move. So that's one way to think about the kind of how they're talking about their failure criteria. And the thing to think about is that on that one, that picture I had up there, the shear strength is not an intrinsic value of the soil. It actually varies with the amount of normal force you have on it. So it's not that you're not going to have some soil deposit that has a shear strength of this or a shear strength value of that. It's dependent on the other stresses that are on the soil mass. So if you're looking at it with more circles, let's say I know my principal stresses. This is force shear stress, and this is normal stress. Let's say this is sigma 3, and this is sigma 1. So looking back at this element of soil, sigma 1, sigma 3, let's say the sigma 1's It's kind of like your normal force on that plate anyways. So what you're looking at is you have a circle. Okay, and when you have this stress condition, if you want to look at this, you have this shear stress. This is your maximum shear stress for this circle. And you go over here, and you go over here, and you have this, that's your shear stress. But let's say we increase sigma 1. This is where it depends on your stresses to determine how your shear strength increases. So let's say we're going to increase sigma 1, leave sigma 3 the same. So sigma 3 stays here. Let's say sigma 1 maybe goes out to here. So you're going to increase this circle to there, and suddenly, as you can see, you have your maximum shear strength is here, which is higher than your circle here. So as you can see, it's not really a property of the soil as much as it is the conditions that the soil is under. Okay, so what I showed you earlier is we have, as you change your conditions, you're going to change your shear stress or shear strength of the soil. So, what's pretty common to do is you want to determine how kind of a wide range of, or you want to determine a function of how your soil is going to react to different, a variety of different normal stresses. So what's pretty common to do is got our same axes here. That's normal stress. This is shear stress. So what's pretty common to do is run a variety of normal stresses, or run a test at a variety of normal stresses. And if we know the principal stresses of these tests, we can plot more circles for each stress level we run the test at. So let's say our test 1 has sigma 3 here. We'll call it sigma 3 1 for sigma 3 in test 1. Let's say it's got sigma 1 here. That's sigma 1 in test 1. So we get a circle like this. It's not a good circle. That's better, a little better. Okay. So then let's say we want another test. We may run it to where this is sigma 3. So sigma 3, 2. And maybe sigma 1 is out here somewhere for the second test. So now our circle is going to look something like this. Okay. And that's 2 tests. Maybe we want to run a third test. So this time we're going to increase this. Let's run sigma 3 here. And maybe sigma 1 out here somewhere. Okay, so draw a circle for this one. Something like this. It's a bit more square than a circle, but you get the idea. It's just more circles of increasing size as we increase our stresses. So, once you run this, the way that Mohr defines failure is if you have a line that's tangent, well not really a line, but a curve that's tangent to all these circles. And failure is defined as this line, so that's your failure envelope, which relates the shear strength and the normal stresses at a variety of stress levels. So his criteria is tau FF, I'll explain what that means in a second, equals, which is correct, yeah, a function of the sigma F. And what these subscripts mean is this is on the failure plane. And that means at failure. So, this function is described by this failure envelope, which is determined by running tests at multiple stress levels and plotting the results and having the failure envelope that goes along with it. So, according to this failure theory, let's say we have all of these circles are failure circles. Let's say we have a soil and it's not on any of these conditions. Let's say it's got a sigma 3 here and a sigma 1 here. Well, that circle doesn't contact this failure surface, so we'd call that circle stable. And anything under this failure surface we're also calling stable. Any circle that touches this fails, and any circle, let's say we have a sigma 3 here and a sigma 1 here. Any circle that goes over this failure surface, these are impossible. So that just shows you the variety of circles we can have and how they relate to that failure surface and what that failure, on the surface, what the failure plane, that's really what that failure plane actually describes. See, if we wanted to put, I guess I might want to draw an element to kind of describe what each one of the circles is showing. This is an element of soil, and then I'm just going to describe any one of these circles as failure. So this would be sigma 1 failure, sigma 3 failure. And then we have this, that'll be our failure plane through this element. Then you have a sigma F, because that's the failure stress on the failure plane. And then you also have the tau F here. So that's really what that looks like. You have these principal stresses, and you have the failure stress and failure shear stress along the failure planes on the yellow. All right, and I'm going to go into one more thing about Mohr's theory, how I showed you how he describes failure along that envelope, but also, I'm going to go into this really quick. We talked earlier, in the last video, this is sigma 1, sigma 3, and you have a circle. This is the part I need. Okay, so let's say we have some, yeah, it's touching. Say we have some failure envelope here. And the way Mohr describes this is, see, this would be sigma 1 acting on the horizontal plane. So since we know how to find the pole, this acts on the horizontal plane. Sigma 1 here, you intersect the circle, so this is your pole. So, since this is the point of failure, according to Mohr, the pole to that point of failure is the failure plane. So this angle here is the angle of your failure plane. But as you realize, that's not the maximum shear stress for this condition. The maximum shear stress occurs here at 45 degrees from your sigma 3. So you wonder why does the failure occur at the maximum shear stress? Why does it occur somewhere else? Well, the thing is, at the max, assuming this failure envelope is correct, at the maximum shear stress, which is also midway between sigma 1 and sigma 3, you have this small distance here between the failure envelope and your maximum stress, and that is you have excess shear strength here. So you're not actually exceeding the shear strength of this material at the maximum shear strength, or at this maximum shear stress, because you have a higher normal stress at that point. So that's why the failure occurs here and not here. Well, now that we've finished up talking about the Mohr's half of the Mohr-Coulomb failure criteria, it's time to talk about Coulomb's half. So, I don't know why I set the chalk in here every time. But the way Coulomb describes failure is you have a shear strength at failure equals sigma tan phi plus c. And what he has here is a stress independent component, which is the C, which is the cohesion of material, and a stress dependent component, which is this term. And you can see it has stress in it, so it's stress dependent. And phi is your angle of internal friction. So you have your angle of internal friction in your soil, which is kind of like the mu we talked about earlier, which is a factor that is, it's just kind of a description of how the particles interact, or the, maybe that's through the roughness or something like that. And that just describes how the friction of the material is. And C describes how the material sticks together. So we have your failure equals sigma tan phi plus C. And plot this. We're not going to plot circles because there's no, we're not running tests for this one to figure out what to do like we did in Mohr's. But let's see, that's C, because that's, this is tau F. So that would be C, because that is, if this is 0, then at 0, tau F equals C. And this is stress again. And this sigma tan phi is a sigma tan phi, so it's going to go, so our failure envelope is going to be F and phi from the horizontal, and that's tangent because tangent is adjacent over opposite over adjacent, yeah, tangent, so opposite over adjacent, tangent phi, right here, that's a phi angle. So this is kind of nice because we have a straight line failure envelope here. So what happens next is we combine Mohr's failure criteria with Coulomb's failure criteria. We get the Mohr-Coulomb criteria. And what that is tau FF, which is the shear strength of the shear strength of the material on the failure envelope, or the failure plate at failure, equals, that's right, sigma FF, and that's on the failure plate at failure, and your angle of friction plus C. So that combines both of the Mohr and Coulomb components of this failure criteria. So that really, so now instead of having a curved envelope like we had in Mohr's case, we have a straight envelope. So this tau sigma. And straight envelopes are easier to work with than curves. So that makes this kind of, it's really nice to work with. So that's our C. Same thing before. This is phi. So now what we have is this is your Mohr-Coulomb envelope, which is kind of a combination of Mohr and Coulomb theories. So just like before, for this theory, any circle which touches this envelope fails right here. And similar to, if you want to put the Mohr criteria back in here, fails along this plane, and also it doesn't fail at the maximum shear stress. So that's the way Mohr-Coulomb failure criteria is defined. So it's nice to use this now because at any given stress level, you can figure out the shear strength available for that sole. And this helps you in design because if you know what your shear strengths are going to be induced by your design, you can figure out if you've got enough shear strength for failure to not occur. And also you can figure out your factor of safety. You know that if you have this envelope and your stress condition is down here, then you've got this much shear strength before you're going to have a failure. So that's your kind of like, you figure factor of safety out through that. And that's just the way the Mohr-Coulomb failure criteria is defined.